My name is MOHAMAD FAHMI, and I will start the presentation with this introduction. Water level control systems are widely used in industrial applications such as water treatment plants, storage tanks, power generation systems, and chemical processing industry. Maintaining the desired water level is important because it directly affects system efficiency, safety, and operational performance. If the water level becomes too high or too low, it may lead to equipment damage, process interruption, or reduced productivity. Therefore, an automatic control system is required to continuously monitor and regulate the water level to ensure stable and reliable operation under different operation conditions. So I will continue with the problem statement. We have found 4 problems in this study case, which is open loop system cannot automatically correct error, water level may fluctuate due to disturbance, the system response is slow, manual control is inefficient. So the water level control system exhibits a slow response when operating without feedback control. External disturbance may also affect the system performance, resulting in inaccurate water level regulation. Therefore, a suitable controller is required to improve the response speed and system stability.
Assalamualaikum and hi, my name is AMIR. I will be presenting our objectives. There are 5 objectives for our project. The first one is to study the operation and components of an industrial liquid level control system. The second objective is to develop the mathematical model and transfer function of the proposed system. The third one is to analyze the open loop and closed loop responses of the system using MATLAB. The fourth objective is to evaluate the performance of P, PD and PID controllers, and the last one is to assess the stability and dynamic response of the liquid level control system.
Okay, for the part system block diagram, as you can see in the picture, you have first the set point, and then the G1, which is the PID controller, and then it goes to G2, where the actuator, and for the G3, it go for the process, and then it go for the output. And before that, it have if not complete, it will go to sensor and repeat the process. The proposed water level control system operates in closed-loop configuration. The controller receives the error signal generated from the difference between the reference input and the measured output. The actuator then executes the control action, while the sensor continuously provide feedback to ensure accurate water level configuration. Okay, for the part mathematical modeling, we have 3 part, which is the first one is actuator. The actuator means converts the controller's electrical signal into physical action, or open or close the system, the control valve, regulates water inflow to maintain the desired water level, or we can call it respond automatically to change in water level. And as you can see, the formula is down there. G2S equal to 0.1 S plus 1. And for the part process, the water tank system, where the liquid level is controlled, receive water flow from the actuator, produce the output, which is the water level in the tank. Its behavior depends on factors such as tank size, inflow rate, and outflow rate. So you can see the function is below there. G3 equal to 1 over to S plus 0.1. And for the sensor is measure the actual water level inside the tank continuously. Send the measured water level to the controller as a feedback signal. Provide information for comparison with the set point. Ensure stable and accurate water level control through precise measurement. So the formula or way actually call it HS equal to 1. And the dynamic behavior of the water level control system is represented using transfer function. The actual and process model were derived and combined to form the overall system model. These transfer functions were used for MATLAB simulation and controller. Okay, for the MATLAB and Simulink model, as you can see in the picture, we're using the MATLAB. The MATLAB or Simulink model was developed to simulate the behavior of the proposed water level control system. The simulation model consists of the controller, actuator process, sensor, and feedback loop. This model was used to analyze both open loop and closed system response.
The figure shows the open loop step response of the water level control system. The step response was obtained by applying a unit step input to the open loop transfer functions. We can see that the response increases smoothly from 0 and gradually approaches the steady state value without exhibiting oscillation or overshoot. This behavior indicates that the open loop system is stable and well damped. However, the response is relatively slow. The absence of overshoot indicates that the system does not experience excessive oscillation, which is desirable for preventing sudden fluctuations in the water level. However, the long settling time indicates that the uncontrolled system requires a considerable amount of time to reach its steady state value. However, the results demonstrate that although the plant is naturally stable, the performance is relatively slow, justifying the need for a feedback controller.
So, I will continue the presentation with peak controller analysis. The proportional peak controller was implemented to improve the performance of the proposed water level control system. In this analysis, only the proportional gain Kp was varied, while the integral and derivative gain was set to 0. The system response was observed for different value of Kp to evaluate the effect of proportional control on the overall performance of the system. The response were analyzed based on rise time, settling time, overshoot, and steady state error, and we choose the test value of Kp is 1, 5, 10, and 20. And this the graph that we got from the MATLAB. So from the MATLAB also, we got the result of rise time, settling time, overshoot, and steady state error of Kp 1, 5, 10, and 20. So the result indicate that increasing the proportional gain improved the response speed of the system by reducing both rise time and steady state error. However, the overshoot increased as the controller become more aggressive. Among the test value, Kp equal to 20 provide the best overall performance, producing the fastest response and the lowest steady state error while maintaining an acceptable overshoot of less than 10%. Therefore, Kp equal to 20 was selected of the subsequent PD controller analysis.
Assalamualaikum. I will be continuing this presentation. For this slide, show the analysis of the PD controller. The PD controller improved the proportional controller by adding a derivative term, which help predict system behavior and improve stability. In this analysis, the optimum Kp value is kept constant, while Kp equal to 1, 5, 10, and 30 are tested. Based on the graph, higher the Kp value make the system response faster, reach the steady state value more quickly. The PD controller also help reduce overshoot and improve the overall system performance. Okay, for the next, this slide shows the performance comparison of different Kp value in the PD controller. Based on the table, the overshoot remains at 0% for Kp value, indicating a stable response. However, as Kp increases, the rise time and settling time becomes slightly longer. Therefore, optimum Kp value is selected to achieve a balance between fast response and system of stability, Overall, the BD controller provides better damping performance compared to the PD controller. That's all for me. Thank you.
Okay, for the PID controller analysis, the PID controller combines proportional, integral, and derivative action to improve both transient and steady-state performance of the system. The proportional term improves response speed, the integral term eliminates steady-state error, and the derivative term enhances system stability. Due to its balanced performance, PID controllers are widely used in industrial process control systems. As you can see in the picture, uh, where test value is Kp equal to 1, Kp equal to 5, and Kp equal to 10. As you can see, the picture that so complete with the coloring full. And for the table, as you can see, you have three value, which is the key value is 1, 5, and 10. And the table have rise time, settling time, and overshot and steady state error for the three key value. And the performance comparison indicate that the PID controller provide the best overall system response. The integral action eliminates steady state error, while the proportional and derivative and action ensure fast response and good stability. Among all test configurations, the selected PID parameter provide the most balanced performance in terms of rise time, settling time, overshoot, and steady state error.
Hello, Assalamualaikum. My name is Muhammad Izzat bin JAMIRUDDIN. So I will continue for the comparative analysis slide. So before looking at the result, let me explain how we obtain this matrix. We simulate each configuration in MATLAB and Simulink using a unit step input, which is set point of 1. And then we run the step info, and then the command in MATLAB, which mathematically extracted the rise time, settling time, and overshot. And then for the steady state error, we calculate the absolute difference between our set point and the final settled output values. And then now let us evaluate the result step by step. So for the open loop system, which is uncontrolled, extremely slow with a rise time of 44 seconds and a steady state error of 1. And then for the open loop system uncontrolled, because it lacks a feedback loop, the system has zero self-correcting capability, making it completely impractical for industrial use. And then for the proportional controller, the result is rise time dropped drastically to 2.28 seconds, but it introduced 2.8 percent overshot and leaves a persistent steady state error of 0.5. Okay, and then justification for that is high proportional gain drive the plan harder and faster, but a POP controller fundamentally requires a constant error and produce an output, hence the offset. Okay, for the proportional derivative controller, overshot is completely eliminated to 0%, but the system slowed down for the for the rise time increases to 21.97 second, and the steady state error spikes to 73.2. And then because of that, the derivative action acts as an anticipatory damper which stabilizes the system, but it adds too much damping and cannot correct steady state tracking error. And then for the optimal PID controller, it achieves the fastest rise time of 1.18 seconds and controlled settling time of 9.1 seconds, and the most importantly, the steady state error is driven to exactly zero. And then how it can be like that, the integration of the assimilated tracking error over time forces the steady state offset to be entirely eliminated, while the proportional and derivative action balance the speed and transit stability. So only the PID controller successfully satisfied both transient and steady state design requirements, which is providing rapid response, stable settling, and absolute precision without any tracking offset. So that's all for comparative analysis.
From this project, we can conclude that this project successfully analyzed the performance of water level control system using MATLAB by comparing the P, PD and PID controllers. The open load analysis showed that the system was stable. However, the response was too slow for practical industrial applications. For the P controller, it improves the response speed, and the PD controller enhanced system stability by reducing overshoot. From all the controllers, we can conclude that the PID controller achieved the best overall performance by providing a fast response, eliminating the steady state error, and maintain a good stability. Therefore, the PID controller with KP equal to 10, KI equal to 1 and KD equal to 2 was selected as the optimal controller for the proposed water level control system